Hello, everyone. Welcome again to another episode of the Focus on Geothermal webinar series. This is a partnership between ThinkGeoEnergy and Enerchange. So, for today's webinar, we are going to feature a topic on geothermal ground source heat pump systems and designing them for heating and cooling applications, also in combination with other possible energy sources like air source heat pumps or solar. And to discuss this topic is Wouter Pire. He graduated as a mechanical engineer at the Catholic University of Leuven in Belgium. His thesis was on the topic of hybrid geothermal designs. And so after a period of research, he started his own engineering firm called Eniad. And since 2023, this company has been the developer and distributor of GHEtool. So this is a cloud-based tool for bore field sizing for both small and complex geothermal systems. And with that, I shall turn over the table to Wouter. Take it away.
Yeah, hi Carlo. Thank you for introducing me. Hello everyone. We cannot see each other, but I hope you're all doing well. I'm glad you all joined us for what I hope will be an interesting talk about one of my favorite topics, namely hybrid geothermal systems. So this webinar will consist of 4 different parts. In the first part, part 0, I will give you a really short context of what we will be talking about. And then we will start with something which is called geothermal potential. And this relates to how you could size hybrid systems. We will talk a little bit about different design methodologies. And as a final part, I will discuss with you a real-life example of how you can use tools to size your own hybrid geothermal system for your next big project. So let's get started with the beginning. So within the domain of geothermal systems, there are quite a lot of different technologies, many of which are also featured in this webinar series. For today, we're going to talk about shallow systems. So it depends a little bit on your country on what's defined as being shallow. In Belgium, it's typically everything above 500 meters deep. So these are typically systems which are used to store energy. So at 100 or 120 meters deep, it's typically the temperatures range from 0 to 25. So we use ground source heat pumps. We can use passive cooling or free cooling. Whereas as you drill deeper, you can actually use the heat directly from the ground. So that's not what we're going to talk about. We're going to talk about shallow storage systems, which are also closed. So we are going to talk about what's called BTEST, borehole thermal energy storage, or bore fields, which are actually holes that are drilled into the ground in which a heat exchanger is placed, a U-tube, a coaxial pipe, through which fluid is circulated, by which we can exchange energy with the ground. And in order to design such bore fields, we typically have the objective that we want our fluids to stay between certain temperature limits. Now, you can discuss quite a lot about how what these limits should be. It depends on your climate zone, on the legislation in your country or your region. In Belgium, typically we set, well, this temperature should be above 2 degrees on average in order to avoid freezing of the ground. And this is because when we freeze the ground, this is not good for the microbiological life in the ground, but also when the ground freezes, ice is an insulator, so the thermal performance of a system is totally gone and it might even fail. So that's why we want to stay away from that 0 line in Belgium. For the maximum average temperature, we want to stay below 17 degrees Celsius, typically between 16 and 18, in order to have still some passive cooling or free cooling, where we can actually use the cold directly from the ground to cool our building sustainably without needing the heat pump to provide our buildings with cooling. And the temperatures that you see, I think I have a laser pointer as well, are then these type of temperature plots where you can see a stimulation period, typically 20 to 60 years, 60 years, especially when you're working with sustainable certificates like BREEAM, etc. And the temperatures, and you see 3 different lines. So we always start with the black line, which is the borehole wall temperature. It's the temperature of the ground at the interface with our borehole. So everything starts from that. And if you're then heating your building, you are injecting temperatures into the ground which are colder than this borehole wall temperature in order to extract the heat. And that's why the red lines are below the black one. And the other way around, it's the case for cooling. So when you're cooling, you're injecting temperatures into the ground which are hotter than the borehole wall temperature, and you can give away the heat you can inject it into the ground. So that's typically how you design bore fields, and now we know that, we can take a look at how we can design hybrid systems. So let's go ahead and talk a little bit about geothermal potential. So to give you the context, imagine you have a very large multi-utility building with 536 kilowatts of heating and 676 kilowatts of cooling, and you simulate your bore field and you find out that you need 130 boreholes, 150 meters in order to sustainably heat and cool this building and stay between certain temperature limits. But perhaps you do not have enough space to drill such a large bore field, or perhaps you do not have the budget for this project, or perhaps you do have the budget, but it's just not financially ideal to do so. So perhaps there are other more economically viable solutions. And that's when a hybrid system comes in. So when we have a building demand that's 100% fulfilled with our bore field, our ground source heat pump, and our passive heat exchanger, we can move towards a system where we have both bore field, the geothermal part, and some other technologies, and typically an air source heat pump, or also solar thermal collectors, or a dry cooler, or waste heat. It does not really matter, but it's just a combination of different technologies that we call a hybrid system. So in the case of a geothermal hybrid system, always one of the technologies will be a ground source heat pump geothermal system. And the advantage of working with hybrid systems is basically twofold. Because we have multiple technologies, we can really optimize and minimize our investment costs. And because all technologies have different strengths, we can use them, we can combine them, and we can avoid oversizing the bore fields, which is typically one of the most expensive components in our whole HVAC system. So that's one advantage. And another one is durable design, so really sustainable design. Because if you're just relying on a single technology to heat and cool your building and it fails, yeah, you don't have anything else. So by having multiple technologies, you have that inherent backup technology already there, making it more durable. But this is all not new, but the main challenge always is, well, how do you design such a hybrid system? Because you can say, well, if we visualize this, we have a bore field which is responsible for 50% of our building demand, but we can also size it like this or like this. It really depends on what you as a designer want to do. And the main challenge or the main question always is, well, imagine that I have a certain amount of boreholes. What geothermal share can I achieve with this investment, with this bore field? And this relates to the concept of geothermal potential. So geothermal potential can be defined as follows. We have a temperature plot here. Imagine we have our big building, but we have a smaller bore field, and we decided, okay, we put a certain amount of percentage on this bore field so that our load is between the limits. And you can see here that indeed the temperatures are strictly between our limits, and that we have designed our bore field in the critical first year. But on the other hand, you see that we do not reach our minimum average fluid temperature yet. So you can say, well, perhaps we can have some extra heating power installed. We can increase the size of our ground source heat pump because we still have some potential for extra power. We can put some extra heating onto this bore field. Now, if we do so, we can end up with a figure like this, where we see, well, we both now reach the minimum and the maximum fluid temperature. So this bore field, we cannot install extra power because we will cross our limits in the end. But of course, we have some extra space for cooling, for heat injection in the later years of the simulation period. In these first years, we also can extract some more energy from our ground. So there is still some potential left, but it is what we call potential for extra energy exchange. We can exchange more energy with this bore field. And if we do so, we finally can end up with a temperature profile which looks like this, where we indeed reach the maximum temperature in every month and the minimum temperature. So we can conclude that this bore field has no potential left. It's fully used. And if we compare these different designs and we start on the left with our bore field who has only still potential for energy left. If you do this in a hybrid design, you have 100% of the installed power. Now, what do I mean by that? If we install a certain amount of ground source heat pump power with a passive heat exchanger, we install it in such a way that we know that we can get the power in each year of the simulation period, because that's what we design it for. And if we know that we have a certain amount of power that we can get from the ground, and we know our building demands, we know exactly what power we should install as a hybrid system, for example, or air to water heat pump. So we do not oversize our system. We have hence the lowest capital expenses, but we still leave some potential behind, some energy potential in the later years in cooling and in the first years in heating. So we can say that this bore field or this sizing methodology, it will give us a lower system efficiency, because typically our geothermal system is the most efficient and we're not tapping into all the potential for the energy exchange, and hence the operational expenses will also be a little bit higher. On the other hand, we have a figure with no geothermal potential left. So we have the highest system performance because we're really getting everything out of the ground. The lowest operational expenses also, but we need to install some extra power in order to tap into the energy potential in these first years. But year after year, we cannot get that power out of the ground. So we need to install more power. We need to oversize our HVAC system in order to tap in this energy potential, making the system bigger as an investment cost. So these are the two different ways to size them. Let us now take a look at the methodology we can use in order to do so. So you can make a distinction between optimizing your bore fields for power, where it still has potential for energy, and also to optimize your system so that it has no remaining geothermal potential at all. And if we start with the power, we have the objective that we want to maximize the power in heating and cooling at all times. So you want to install a certain amount of power of which we know that we can use it throughout the whole simulation period. So if we take a look at an example, the same building as before, we said, well, it was 536 kilowatts in heating, 676 in cooling, but we can only drill 80 boreholes. Now, if we have the load duration curve of the building below, so for the people who are not aware of this, the load duration curve is when you have the hourly heating and cooling value for each hour of the year of your building, and you arrange them from large to small. That's what you can see on this figure. And you see, if we do this optimization, that we can get 259 kilowatts in heating and almost 170 kilowatts in cooling. And the hedged area is the corresponding energy that we can extract with the ground. And it's just this unhedged area, let's say, that our hybrid system should be able to provide. So we have indeed a beautiful aligned system where we do not oversize it, because we know this part is for the ground and the other part is for our hybrid system. So this is if we optimize for power, and then we end up indeed with a temperature profile which is limited in both maximum and minimum. Now, if we optimize for energy, we have another objective. We now want to maximize the energy that we can inject in or extract from the ground over the whole simulation period. So this means that if we install a certain amount of heating of our ground source heat pump, we know that this will lead in the end to the largest geothermal share in heating, but we cannot be sure that the power we install, that we can use it at every instance, in every year and in every month of the simulation period. So these are the figures that tell the story. So what you can see here is it's a 2-axis figure. So you have the time horizon on the x-axis, you have the power on the right, and the energy on the left. And what you can see here, that year after year, our peak heating power drops. And this is because in the slide I showed you before, there is an imbalance. The ground cools down year after year. So year after year, the amount of peak power we can extract from the ground will be lower. And also the full red line is the energy we can extract less and less energy from the ground for our heating after the years. So year after year, our hybrid system should fill in the gap more and more. And in cooling, it's the other way around. So because of our imbalance, the ground cools down year after year, leaving more and more potential for cooling. So that's why the cooling peak increases year after year, and also the cooling energy. So the amount of energy we inject into the ground increases year after year. So this is a really interesting graph, which tells you a lot about how your system will behave over time. So it's not a static picture which is applicable to all the years. It really evolves over time, and it gives you quite a lot of insight in how you can size a hybrid system. So let us now take a look at one particular case and how you can play around with this to come up with some interesting results. So we're going to do that with GHEtool. Now, GHEtool is a novel board field sizing tool, which was originally founded during my master thesis in 2019 at Catholic University of Leuven in cooperation with Boydens Engineering, which is now part of the Sweco group. And after the years, it has been developed in collaboration still with these parties. And last year, we brought it out as GHEtool Cloud, where we really have the philosophy that we want to move away from designing the board field as being a component towards the philosophy that we want to design the board field as being part of the system. So we want to go towards a system design where we have made methodologies for hybrid systems, which we're talking about today, about active and passive cooling, hydraulic calculations, pressure drop, pump energy, also regeneration, etc. So we really want to facilitate the energy transition from the geothermal perspective, and we want to use our tool as a catalyst for geothermal innovations. So GHEtool is open source based, so the methods and the assumptions we made you can find 100% transparent online. And we work together with quite a lot of partners all over the world. So both research institutes working on newer methods and models and optimizations, but also, which is very important, with partners from industry. So companies who are developing new technologies on their own, new heat exchangers, new antifreezes, etc. We want to work together with them to develop models, implement it in the software, so people, designers, can design the system with actually the newest innovations and models in the industry. And that's what we're trying to achieve with our software. So if we take a look again at the example I showed you before at this multi-utility building, where we know, well, we need 130 boreholes in order to fulfill the whole heating and cooling demand. But we find out that on a project side, there is only space for 90 boreholes. So let us now take a look how you as a designer can cope with this problem and use the methodologies from before to size your system to be able to deliver this. So let's first put our full building loads onto this 90 boreholes. So we have a bore field with a grid of 10 boreholes by 9 boreholes. And you can see that we significantly crossed the temperature limits, both the maximum and the minimum temperature limits. So we see 90 boreholes is simply not enough. We need to go for a hybrid system. So let's do that. We will start by using the methods to optimize the power. And what you can see here, I want to draw the attention to the temperature plot below, is that we have peak shaped, let's say, the building demand for a geothermal system in such a way that we stay between the temperature limits and that we have 78% of geothermal share in heating and cooling, which is the light blue circle. And we have 100% of our building demand also installed. So we have 536 kilowatts in heating installed, of which 247 geothermally, and the other part is with our hybrid system and the same in cooling. Now this is the first starting point, but perhaps you can say, well, 10 by 9 boreholes, it's what's possible, and we can fit it onto this field, or we have the space. But perhaps there is an economically more interesting solution. So we can say, well, imagine we make it a 9 by 9 grid. So we go for 81 boreholes instead. And then we have this figure. So not much has changed there. Our total installed power is still the same, but we dropped from 78% to 74 and 73%. Still staying between the limits, but here also in the low duration curve, it was that the geothermal power was lowered a little bit. So what is the insight you can get from this? Well, we saved 10% on our investment cost of the bore field, and we only lost, or only its relative, lost 5% in geothermal share. So perhaps can you say, well, we do this once again and we go to 9 by 8. And here we are at 70% and 68%. So now we already lost 10% of our geothermal share by making the bore field smaller. And you will see that if you keep decreasing the bore field, its effect will become significantly even more. And this has also to do with the low duration curve. So as you can see, if you lower this power even a bit, that the amount of full load hours, or due to the amount of full load hours, the total energy yield will also decrease quite a lot. So perhaps you can say, well, the previous slide had the 9 by 9 is economically more interesting. You can check that with total cost of ownership analysis, etc. So perhaps we should work with that one instead. Okay, so let's use the 9 by 9 then and optimize for energy, just to show the difference. And you can see the difference really clearly if you take a look at the temperature profile. So this is totally different because now we're reaching the minimum and the maximum limit at every month of the simulation period. And you can see that with the same investment cost for a bore field, we are now at 84% of geothermal heating share, right? Instead of 73 from the optimized power, and 92% in cooling instead of 74%. So this is a really interesting finding that since our bore field is typically the most expensive part in our HVAC system, that by keeping the investment cost the same and just installing some extra power, that we can achieve a way higher geothermal share. And this effect, I'm sorry, my phone was not quiet. But you can see that the total installed power we have is way higher. So we have installed 148% of what we actually need, because now our bore field, our ground heat pump is also 510 kilowatts, and we need even more to be able to fulfill our heating and cooling demands. And this you can see on the figure on the top right. So you can see that year after year, the peak power in heating decreases, and that's because of this imbalance. So we install this 510 kilowatts, but after 5 years, we can only use 400, and after 10 years, we can only use 350 kilowatts. So we install this ideally in order to tap into all the geothermal potential, but we can only use that power for a couple of years. So perhaps we can say, okay, let's optimize for this energy, but let us not go all the way. Let's limit the amount of ground source heat pump power that we install to 350 kilowatts, let's say. And if we do so, we end up with this figure. So I want to draw the attention to the geothermal heating share. The cooling is the same. We dropped from 84 to 83%. So we lost a little bit of geothermal share on average, because, and which you can see here, these first 3 years we're not stepping into all the energy potential. But we decreased the oversizing from 148% to 117%. So it's way more feasible from our heating total investment cost. And if we take a look again at the figure on the right, you see that the power we install, the dotted line, is 350. We can use it, quite a lot of years, and then it starts decreasing once again. But it stays the constant because we're not tapping into all the geothermal potential there. And in cooling, it still is the same. It increases year after year because of the imbalance. So perhaps we can still go a little bit lower. Let's say 250 kilowatts. And you can really play around with this. And if we go for 250 kilowatts, we see something really interesting happen. If you take a look at the figure on the right below, you see that we reach the temperature or the minimum temperature only in the last year of operation, which means that the peak power we install, we can always use. And in the baseload energy in heating is also the same. It's only in cooling that year after year we can inject more heat into the ground due to the imbalance. And this is really interesting because now we have 100%. We do not have any oversizing for our geothermal system. We can use with 250 kilowatts, we have 78% of the heating instead of 48 when we installed twice as much, 510 kilowatts. And this is due to the fact that because we have oversized our cooling here, which is not that big of a problem because it's passive cooling, so it's just putting in a bigger heat exchanger. We can inject more heat into the ground year after year, making sure that our ground cools not down that much and that we can have a very good heat extraction rate until the last year. So these were 6 simulations, and let us now summarize that. So I created a table for you where we have the bore field size, the methodology we used, the ground source heat pump, and the passive cooling power we install, the energy share we get with that, and then the total installed power. So we started by a bore field of 10 by 9 with 247 power on the ground source heat pump, 177 for passive cooling, and we achieved 78% for both heating and cooling. We said, well, we made this a little bit smaller, and we see that the geothermal heating and cooling share, it dropped a little bit, but the installed power, of course, stayed the same. We decided to do this once again. It dropped even more. And then we said, well, this scenario is perhaps, just as an example, not financially ideal. We will continue working with the 9x9, but we now optimized it with the energy in mind. So what you see here, and it's really interesting to compare, that the amount of ground source heat pump power we install with this methodology went from 224 to 510 kilowatts, and cooling the same. And we went from 73 to 84% geothermal share, and from 47 to 92% of geothermal cooling. So with the same investment cost, again, as with the optimized for power methodology, we were able to achieve way more geothermal share. But of course, we oversized our system quite a lot in cooling, but especially in heating, which is way more expensive. What we then said as well, instead of having this so big to 510, let's drop it down to 530. We see that our geothermal share in heating dropped only 1%, but our total installed power, which is related to the investment cost, it dropped significantly. And the same is can be said when we dropped even further to 250 kilowatts. We have 78% of geothermal share with no oversizing of our heating system. And I just want to draw the attention to, we have no oversizing in this methodology, and if we did it with a 9x9 and we optimized for power, we also do not have an oversizing, but the geothermal share differs by 5%. And this is because if we optimize for energy in this way, we oversize, in this case, our passive cooling, so we can inject more heat into the ground over the years to come, not so much in the first year, but in the third and the fifth and the 10th, and etc. And by doing so, we create some extra room for some more heat extraction, so for more geothermal heating. And that's why this 9x9 optimized for energy gives us a higher geothermal share than the 9x9 optimized for power, even though they have the same installed power for heating, because they have different installed powers for cooling. And what's also interesting, if we do this for this methodology, that we have with the 9x9 methods, 9x9 bore field optimized for energy, the same energy yield in heating as with a 10x9 optimized for power, with almost the same power as we install here. So just to say that you can really play around with these methodologies, you can set in limits, you can optimize it. It does not really matter, but you can really get into a really good idea of how such a hybrid system will behave in practice and what the efficiency will be. Now, if you think that this is an interesting topic and you want to know more about it, we actually wrote 3 articles over on our website on this topic. First on geothermal potential, then on the methodology, and then the example I just showed you. It's free. You can visit the website and read the articles if you're interested. And then if you want to experience or try out the software, please go ahead. You can schedule a demo call with me. We will be more than happy to see how we can help you with your project. And if you have any questions related to the presentation of today, I will be more than happy to answer them. So thank you for your attention. I hope you found it interesting, and I'm looking forward to it.
All right, thank you, Wouter, for that presentation. I find it very interesting that you actually can play around a lot with bore field designs, and they're actually quite flexible.
Yeah.
So for the audience, for everyone who's still here with us, feel free to send in your questions. There should be a questions tab somewhere in your webinar panel. So just type in your questions there and we'll get to those. We still have like 20 minutes to get through the questions. So we can start. We can start with some of the questions I already have. Your simulation tool, does it have any assumptions on the type of heat exchanger that is used for the borehole? Like, is the assumption here a U or W type of heat exchanger, or is there a way to design this for, say, coaxial heat exchangers?
So the way GHEtool works, as with almost any other design tool, is that you can select the heat exchanger single U, W, you can change the grout, you can change the amount of glycol you put into your system. You really have a lot of flexibility. But yeah, this was just about when you choose how you want to have the borehole internals, how you can then come up with a geothermal or a hybrid design. But yeah, there is quite a lot of flexibility also in that domain. Yeah.
Okay, so somewhat also related to that, what are the sort of input parameters and also boundary conditions that you need to have before you can start this kind of simulation?
The boundary conditions, because it's an optimization method, you need the temperature limits, and because it will optimize the load between those temperatures, so the minimum and the maximum average fluid temperature you need. That's a boundary condition. For the inputs, this type of method starts with you selecting a design. So depending on your project, you can, for example, even upload a map with the coordinates where you're going to drill the boreholes. So that's of course an input you need to have. Where am I going to install my system? The amount of boreholes. Then you need your building loads, which you are going to optimize. And for this type of methodologies, you need to have it on an hourly level, which is really important. So your building has to be simulated one way or another, or you will have to have measurements, because you can only optimize when you have that high of a resolution to play around with. So you need an hourly temperature profile for that. And then as I said before, select if you're going to work with a single or a W tube, or which type of grout, etc., etc. So the typical design parameters for every borehole project. Yeah.
Okay, a lot of questions are not trickling in. There's one here that I think we should address like quite early on because it's one of the earlier. It's part of your earlier slides. So please redefine optimize energy and optimize power scenarios. I mean, I have to admit I was also quite confused with this before I read your article. So I guess we could go over it again.
It's indeed a really how should I say it? Vague concept. So I will go towards a slide which I think will help. This. So basically, you can see it here. So if you optimize for power, what you want to do is you want to say, well, I will install as much geothermal heating and cooling as possible, but I want to make sure that if I install 200 kilowatts in this case, that I will get this 200 kilowatts at all times. So we need to make sure that we stay between the lines, of course. And in cooling, we say, well, we install a certain amount of power in order to not cross this limit. And this means that year after year, we are limited by the power we installed. So that's why we cannot go any higher here. And in heating, it's the same. We see that we need to install a certain amount of power in order to not cross the limit in the end. But this also causes us that we cannot extract more heat even in these earlier years. So that's if we optimize for power, we need to make sure that we have this power at our disposal during the whole simulation period. If we say, well, I'm not worried about installing some more power if I can get more energy out of the ground, because we could exchange more energy, and we can end up in the end with an extreme case like this, where we say, well, year after year we are going to touch these limits. So what we are going to do is we're going to install more let's start with the heating, more power for a geothermal heat pump. So that in these first years, we're also going to touch the temperature limits, so the minimum temperature. And by doing so, we can exchange as much energy with the ground. But as we saw in the example, we need 500 kilowatts in order to tap into this potential here. But year after year, we cannot use that power anymore because we are limited by that temperature limit. And that's basically the difference. So if we optimize for energy, we really try to get as much energy as possible, and we do not care about how many how much power we need to install. We really just want to get into that energy. And if we optimize it for power, we want to make sure that the power we install we can get at all the times. So that's indeed a little complicated concept to get your head around, and it took me more than a year to find a way to make both optimizations work. But it's really a different way of looking at how you design systems. So read the articles if you want to know more about the methods. It can help, I think, Carlo.
Yeah, it does take some time to get your head wrapped around the concept, but I think this slide summarizes it pretty well. Like lower OPEX versus higher CAPEX, oversized system versus something that just maximizes the power of the pump that you're using.
Yeah, neat.
Okay, some more fairly basic questions. Is there any implication on the useful life of the reservoir when you use the optimized energy scenario?
Is there some effect on the lifetime of, or what do you mention?
I mean, the useful life of the reservoir. Do you think that there will be a faster decline under an optimized energy scenario?
Not difficult to say in general. Let me think about it. I don't think so, because in practice, when you optimize for energy, what you will do is you will have a control strategy that says, well, the temperature is below our limit. We will put it onto our hybrid system. And the same you will have when you design it to optimize for power. The inherent difference is that in this case, in the first years, you cannot extract more heat from the ground because you're limited by the power. If you have a very bad control strategy with the figure on the right, optimized for power, where you have 500 kilowatts, you can indeed cool down the ground way faster because you have that power. So you need a control strategy in order to make sure that you do not cool down the ground too much. But it really comes just down to how you control it in practice and not so much on how you design it.
Yeah. So I guess it's not a matter of the scenario, but rather the control system that you have.
Yeah, indeed.
Okay, then let's get to some of the more something more specific on your presentation. There's a question here on the slide showing the 9x9 borehole field for the optimized energy scenario.
Yes.
So he is asking about the plateau for the blue line. It seems to have plateaued twice. What was the cause of the first plateau?
Plateau twice.
Yeah. I mean, I can see it. It's a small change, right?
Yeah. It's a really technical question. I will try to explain it. So the way this method works is it will optimize not every hour but every month. So it will take the hourly profile. It will make a low duration curve for every month in the simulation period, which is quite a lot. And then in every month it will say, well, I want to stay between the temperature limits. So if I decrease my peak cooling, how much energy can I still extract? And that's what it do for all the months in the simulation period. And because you have that difference in resolution, so you have an hourly input, but you work in the methodology with a monthly resolution, which is, by the way, just for numerical reasons. You can do it hourly, but then it will take an hour to calculate and not 1 minute. Because you have a discrepancy between an hourly input and a monthly calculation, you will have sometimes numerical numerical, how should I say it, numerical issues that cause this line. So I think if you would go for an hourly optimization, it will increase only slightly, but when you go to a monthly resolution, it looks like it plateaus, if that makes sense. Yeah.
So I guess this is just a very small variation in load because of an hourly optimization.
Indeed, you have to look at the hourly profile to see how it correlates with the monthly assumption. But yeah, it will not make that much of a difference. It's just a numerical thing. Yeah. But a very good question.
Yeah. Okay. Also a very sharp observation. Okay. How does the model of the heat pump factor into the simulation? Do you use a fixed COP number, or is there a way to vary COP based on the supply temperature?
So the way it is done now is by using a constant SCOP. We're working on advancing towards selecting a heat pump with part load data and temperature data. We're discussing with the manufacturer because it's really sensitive data, but now it's a constant SCOP. So that has also an effect on the way the ground cools down, because you will have the effect that the efficiency will be lower if the temperature drops, and this will also have an effect on the optimization strategy. But yeah, that's next level, let's say, effect that we will include in the future. Yeah.
How does your simulation factor in costing? I think you mentioned quite a bit about this when it comes to the heating capacity and the cooling capacity, but can you explain a little bit about how this can help project developers with the cost of the system?
Yeah, of course. So when it comes down to the economic optimization, which is actually next to power, energy, the third one we're going to develop, it's typically a trade-off between investment costs and operational costs. And once you decide, well, we're going to drill a certain amount of boreholes, which will have a very big investment cost, the economic optimization comes into view. Well, if we install a little bit more heating and cooling power, can we achieve a higher system efficiency? So if we have a higher geothermal share, we will have a lower energy bill in the end, and this will be the way how designers can use these optimizations to find really the trade-off, which is really country and project specific, between the size of the bore field on the one hand, but also the size of the ground source heat exchanger, or the passive heat exchanger and ground source heat pump, where the trade-off is between the investment cost there and the operational expenses from the energy component.
Okay, there's another fairly basic question here. Can this tool be used for medium to deep geothermal systems up to say 1,000-meter boreholes?
In the end, it can, because we are able to take into account different ground layers as well. The thing is that it's based on something which is called G functions, which assumes that the ground is homogeneous. So if you have a ground where the let's say the temperature gradient is not that constant, or you have quite a lot of changing in thermal conductivity, the accuracy of the model becomes less. But theoretically, you can use it for 1,000 meters is deep, but 500 meters should work. But if it's just rock all the way down, it's another thing. But if you have quite a lot of different layers, and especially, for example, permafrost regions, it's always hard to model that with such tools.
Okay, so that's also interesting, because the assumption here is that the ground has homogeneous characteristics.
Yeah, that's a basic assumption behind all the models related to ground source heat pumps. The only way to get around it is by actually doing numerical simulations. That's just the way these things are modeled in using G functions. Yeah.
Okay then, so you discussed quite extensively about like hybrid systems, how geothermal system can be combined with another source of heating or cooling. But what is the implication for the complexity of surface infrastructure, surface installations? What is easier? What is simpler in that regard?
Yeah, that's also a good question. You can of course make a system as complicated as you want as a designer, but in the end, not so much serving costs, but the risks that there is something wrong with the surface because a valve is set in the wrong direction. Yeah, it's real. I think when it comes down to hybrid designs, you can. I do not have a special slide for that, but you can come up with hydraulic configurations and control strategies which are really simple and just temperature based. So if the temperature of the ground goes below this, well, we put on the other technology, and then it's not so much on the design of hybrid systems, but the design of the hydraulic system. So how are you going to arrange all the technologies together, putting in the different valves and controls, etc. It's more related to that part, less than to the design of the hybrid source, which is a little bit independent from how you design it hydraulically. You can come up with 10 different hydraulic strategies for having the same hybrid system. So your question is more related to good hydraulic design more than good hybrid design, I think.
Okay then. What else? I mean, we still have a couple of questions here. Um, for those asking about the recording of the webinar, we'll be uploading it as well, say in a week. And also they were asking about the series of articles you posted. I believe they're on the GHEtool website, right?
Yeah, you can find it under knowledge base, and also on a YouTube channel. If you want to hear me talk again, you can also find it there. Yeah.
Okay, so there's a follow-up question to the COP question. Does the software provide not only the calculation of building load, but also energy from the ground to the point where one could use a detailed performance curve to estimate total building load and the electric power needed to supply that load?
The electric power, it does not explicitly mention that because we use a constant SCOP. You can directly calculate it when you have the energy. So when you have the, let's say 500 megawatt hours of heating on average per year, and you know the SCOP is 5, you know that it's 100 megawatt hours of electricity. So you can calculate it that way. It's not explicitly mentioned in the tool. I think that's an answer to the question. Or perhaps I do not understand the question.
I mean, I think it's mostly a question of the electrical power needed to support the system. I think that should be fine. Um, what is there a way also to incorporate, say, I'm not sure if it's common practice, but is there a way to incorporate boreholes that are not vertical to the system, to this kind of simulation?
Boreholes that are not? Sorry.
Not vertical.
Yeah, it's possible. So we have a very detailed way of putting in your borehole. So every borehole can have a different depth, different bury depth, different tilt, and different orientation. And we're going, and that's because of the beauty of these G functions, which were developed at the Polytechnic University of Montreal. You can really model it as accurate as possible. So we're not trying to find something that looks like it. We're really trying to, we are really working with the design you enter. So yeah, you can work with tilted boreholes in all different directions. Yeah, no problem.
Okay then. I mean, we're almost we're almost out of time, so I think to wrap up the discussion. Can you comment on, say, the the trends or has there been an increase in demand for geothermal boreholes, geothermal bore fields for heating and cooling, say even in Belgium or in the Netherlands or in wherever whatever site you've studied? Can you comment on say how
Well,
have clients approached this kind of thing?
so it changed radically last year. So the thing is, there was indeed an increase in demand in Europe, Germany, the Netherlands, etc. But with the energy crisis and with prices skyrocketing, its demand decreases a little bit. And then there were quite a lot of legislation that changed. For example, in the Netherlands, which was the second biggest geothermal market in Europe, the legislation was changed rather dramatically up until the point that there are almost no geothermal installations installed now. I said almost no, none, but relative to what it was before. In Flanders and Belgium, on the other hand, it increases. In Germany, it was decreases. It decreased also. It increases now again a little bit. So it's really changed because of some legislative parts, but in the end, it's a really robust and proven technology for the sustainable heating and cooling. So different governments are working on ways to, again, try to facilitate this type of solution, but it's difficult to find the balance between being sure the environment isn't harmed and facilitating a technology which is inherently rather expensive. So but I think it will increase again over the next years when the market is again settled and everything is back where it was before.
Yeah, I mean, just like in the wider geothermal industry, it's usually not a matter of technology. Technology always progresses.
Yeah,
It's more capable of it's currently being used for.
yeah,
But the
indeed.
hurdle is always more financial or business or legislative or the lack of incentives that promote this kind of technology.
Yeah, indeed. Financial is not that much of a problem for this type of hybrid systems because if you design them, they're really cost efficient. It's not that easy to design them, but tools like this can help. But yeah, once the legislator puts in barriers, it's always harder to find people who want to go the extra mile. But that's always the case.
Yeah, well, and on that note, it might not be that positive, but for those who are interested in the topic, there's plenty of material on it that you can go check out the website of GHEtool. There's some really nice material there on geothermal bore fields. So thank you for the time, Boda. Thank you for that really good presentation. It was very interesting.
Thank you for having me.
Yes, and thank you as well to the audience. We don't have a huge number, but they were very engaged. So thank you for the attention, thank you for the interest, and thank you for the time. And have a happy weekend, everyone.
Have a nice weekend.
Bye.
Take care.